Yeah, it sounds.
Okay, so so this talk is now slightly different to the other ones. This is not about creating forecasts, but just about evaluating forecasts. I have to say, well, I should have had my co-author here. Kevin Berg was postdoc in Siegen in Germany. He kind of worked with me on this topic, but now he left for industry. But basically, everything I'm presenting to you now is more or less done. So we just have the working paper. We already submitted it to a journal, and in the next few days I will put it in archive as well. So it's more or less done. Say at least the first step. And this is just on forecasting evaluation. So I think, the first slides, most of you will be familiar with it, but then it will become a bit more useful for you. Okay, so the setting we're going into will be the following. We are creating a forecast, and we have an interest in a random variable y, which is a multivariate random variable. So you could just think in the most simple case, take a bivariate one, which is could be, for example, just like Matteo just said, well, the maximum temperature of, say, tomorrow and the day after tomorrow. This is the thing you're interested in, and you want to have a forecast. And the thing you're interested in is, in fact, the bivariate distribution in this case. And this we will denote always by y, and the corresponding distribution function will be this fy. This is the thing we are interested in this study. In practice, of course, we have the forecast that we never observe the y, we just observe an observation of it. So just one possible outcome in the bivariate case, just the temperature of tomorrow, the maximum, and the load, and the next day's maximum. Of course, what do we have in practice? So the standard thing we discussed, I think, in at least a couple of talks in the last week, the standard point forecasting. Here we have an estimator for a specific characteristic of the y, which is usually the mean or sometimes the median, and mainly it's evaluated based on the forecasting error. It is just, say, our forecast minus, or the other way around. And we know, of course, we can do evaluate these kind of properties strictly proper. The mean by the MSE, or RMSE if you want, and the median by the ME. This is quite well known. And this is standard point forecasting. This is what we have done the last couple of decades. Then we noticed, well, we need something better, so we went for probabilistic forecasting, which basically means just everything beyond the point forecasting. In the most simple way, it's just forecasting intervals, or something like mean plus standard deviation. In a more sophisticated way, it means forecasting the density of the next day's thing. And this is mainly the marginal distribution of the Fy. So our multivariate object has some marginal distributions, which we will denote Fyh for h from 1 to capital H. With capital H will be always the forecasting horizon cost. So capital H will be the dimension of the object we're interested in. H for forecasting horizon. And here we have multiple methods. We've seen lots of quantile forecasting things, and there we have also strictly proper evaluation methods. And I think the most important one on this scale is the so-called continuous rank probability score, the CRPS, which is in fact the quantile loss or the pinball loss across an equally spaced grid of quantiles. So, like in the global energy forecasting competitions in the 2014 and 19, they used the 99 percentile grid, and if this grid goes, the distance between this grid goes to 0, basically we're converging to the CRPS. And in fact, I noticed in a couple of papers even they report the CRPS, but in fact what they do is just computing this kind of thing and just average, which is, I think, okay, if you have 99. Okay, so this is what we have done so far. So this is, say, this current state of probabilistic forecasting. We had just one talk, and this was the Jeff rule. yesterday who mentioned something beyond, say, forecasting the marginals. And this is also what is, say, the main problem and what's the talk about. The problem is that if we just have forecasted the marginal distribution, we are ignoring the dependency structure in our forecast. And especially, well, there are a couple of applications where this is really important, and here I have chosen one thing, which is industrial load forecasting, where you have something like a company which produces, I think this is paper, it produces, and then sometimes the machinery breaks down and you have to maintain for some reason, and then it's running again. And then there's some periods where it's more likely that the machine goes down and has to be repaired, and the other ones, yes, not. And so if you do just a quantile forecast, it looks like this, and it's not much informative. You just know a bit, well, when periods where it's more likely to be down, but what you really want to know is kind of the trajectories, how they could look like. And therefore you need, of course, the dependency structure for evaluation. And this is what we try to investigate a bit more. So what we need is, we need a full forecast fx for fy. So x would be our forecasting distribution, and y is the thing we're interested in. Okay, what do we have in literature? Now I just summarize a bit what is known, what do we have. So one evaluation score that is available in literature is the so-called energy score. Well, it depends on our forecasting distribution, this fx. So just assume we have this distribution, however we just got it, and our observation y, and this is the definition in the energy score. I'm not sure if you ever met this kind of thing, but essentially you have two terms in this definition. The first one looks very familiar to the thing we are usually evaluating, which is just the distance between our random variable itself to the observation. In the Euclidean norm, which is, say, a standard norm, and to the power of beta, where beta is just a kind of parameter, which is usually chosen equal to 1. So if you see the beta, just think about 1 for the first moment. It's just, and it's also the case that the energy score for beta equal to 1 and h equal to 1, so in the univariate case, is equal to the CRPS. So it could be regarded as a natural generalization of a CRPS, which works quite well in the univariate setting. But so this is the first term, we just measure, say, the deviance from the observation. And then we subtract something which is a bit odd at the beginning. If you see it the first time, it's the random variable minus its IID copy, also in the same norm as before. And this is subtracted from this part here. And this measures, to some extent, the dependency structure within the random variable. So here, in this part, all the dependency information of our forecast goes in. So this is more about hitting, say, the mean level correctly. And this part is about what is about the dependency structure of our paths that we are forecasting, just intuitively. You will understand this later on better and better. So this is the energy score. This is, it was introduced by, I think Tim Nighting did this in 2000 something. And the important part is that this score is strictly proper under some restrictions, namely that your random variable needs a mean. So, but if you have a mean, this thing is strictly proper. But I think almost everything we are modeling has a mean, so we don't have extremely heavy tail stuff that we are considering. So this is what we have. So this is, of course, one option we could use for applications, and Jethro yesterday also applied it. Another option we have is the so-called Barry-Ram score. This is the second one we applied yesterday. This is basically motivated from spatial statistics, where you have the so-called Barry-Ram estimator for spatial dependencies. And this is its definition. It has some similarities in the sense that it's a kind of difference, but overall it looks quite different. The important part about the Barry-Ram score is that it's not strictly proper. It means that so it can't always identify correctly the true distribution, and especially this is the case if we just have to take the true distribution but shift it by a certain amount. We just shift the mean, and we get exactly the same y-gram score, but of course it's then not the true object. So this is just the most important property of the y-gram score. Okay, what do we have else? Then we have the so-called log score, which is essentially nothing else than taking the log of the forecasted, our density of our forecast. So what we need is we need a continuous random variable, we need the corresponding density, we can take the log, and we get the log score. The good thing about this thing is this is strictly proper. If our random variable has density, of course, the back density, and yeah, so this is in general a good property. The problem is that in practice we don't have this, well, it depends on your modeling approach, but especially for very complex models, we often don't have the density forecast available. If we have a parametric approach, we often have it, but in quite a lot of applications this is not the case, but of course this is, could be discussed. This is a bit the problem with for the application, with a log score. However, well, if you choose, for example, this density equal to the normal density, multivariate normal, basically this thing boils down to the David-Sebastiani score, which is something which should look familiar to you, which is essentially the likelihood of the multivariate normal distribution, which is another special score which in fact just evaluates the first two moments of our forecasting distribution. So this score is minimized if the mean and the covariance matrix matches the corresponding forecast. This is the David-Sebastiani score. It's also sometimes used because it's quite simple and it's more say old-fashioned, but I think it was the first approach to these kind of multivariate evaluation things.
Florian, the interest also of the log score is that it's a local score, since you only need the value at the observation.
Yeah, right? You're right. Yeah.
Which brings also some nice
yeah, that is what we could be everything. Yeah, you're right.
It has also some disadvantages to your right, because it's about when you have very low probability, it can be very unstable in practice.
Yeah, this is the problem in general with the log density, especially when there are some approaches where you say, well, I don't have the density estimate, but I want to use the log score for evaluation, so I have maybe just an ensemble, and then I apply some kernel density estimation or something like this, but they are of course very rough, and it depends a lot on your estimation method based on the sample, and you're getting a lot into problems with these kind of things.
There are some trimmed versions so that you get a robust estimator of the log score, so that you prevent this issue.
But then is it still strictly proper if you start doing that?
I forgot.
I guess it's more an applied thing.
Yeah.
Well, yeah, but and that's basically everything we have in literature. So these scores, and there's nothing really more out there. So as a summary, only energy score and log score are strictly proper. But within this paper, we decided to ignore the log score because we think it's not very useful for practice. But of course, it's open discussion, so it might be worth to look further at it as well. But here we just decided to ignore it and to keep track of the other ones. So about the energy score, which is strictly proper. Yeah, so at least from the properties that I studied so far, it seems that the energy score is preferable, but it's hardly applied. We've seen there are maybe 10 papers out there which kind of apply them, but like Jeffrey did as well. But they are really not the lot paper which use the energy score. And one of the reasons is due to this working paper from Pierre, where they kind of stated basically that the energy score is not sensitive in changes in the dependency structure. And what they did is a very simple simulation experiment. They assumed a bivariate normal distribution, fixed the mean. Well, they changed. They considered not just changes in the dependency structure, but also in the mean and the variance. But everything was fine. And the main issue they raised was in the dependency structure. So consider just the bivariate normal distribution, mean and standard deviation equal to 1, and just the correlation is the thing you want to kind of measure. And now we fix certain correlations. Say the true correlation of our distribution is 0.4 in this bivariate normal distribution, and then we have a certain forecast. And we see, of course, if the forecasted distribution is 0.4, the energy score is minimum. Yeah, so this makes sense. But if we forecast instead, for example, something with correlation of 0.0, the relative change in the energy score with respect to the true model was about, well, less than 1%. And this is the issue. What they raise is well, the relative change is just less than 1%, even though, well, the 0.4 correlation and the 0 correlation, it's easy to see by eyes that there is something going on, and this is not very nice. So the conclusion was, well, by looking at this relative change in the scores, it's not sensitive, and that's the dependency structure.
So isn't it true that, like Sylvain said yesterday, what's important is not really the value of the score, but the ranking. And so like even if the score is not very sensitive to all these things, but if at the end it always ranks the true distribution.
Yeah. So
that's where Florian is going at.
Yeah. So I'm not saying that this. So we will kind of see that this is not really the best way to evaluate and looking at the scores, but basically. This is more their conclusions, but it's just a working paper, so it's never appeared in. But still, it's quite highly cited, especially from people from wind energy and so on, to say exactly the statement of Jeffrey and say, well, this is not sensitive in the dependency structure.
So, I mean, that's very nice that you mentioned that in the work of Florian, because the point of this was first on page 2 of the paper as an illustration, because people take scores at face value, and then they should be aware of this sensitivity issue. And maybe an expert statistician would say, okay, it's not the face value that's important, but not the most important result in the paper was more about the effect of dimensionality and to have an upper bound on any kind of difference that you get.
Still, I think this graph is the most. So most of the slides you got because of this graph.
And I think it's nice that it triggers the discussion.
Yeah, that's completely right. Okay, so this is what we knew. So our idea was, well, we have to do something and then try to find a score which is then sensitive in the dependency structure. And because in this paper also they discussed the change in the mean and variance, and then everything seems to be fine, we came up with a very simple idea to construct so-called marginal copula scores. And the idea is quite simple. Basically, well, we know if we have a multivariate distribution and it's continuous, we can kind of split it into its marginals and into the copula, and this is what we did. And then doing some evaluations for the marginals and for the copula separately. So this was, say, the core idea. Nothing really special, and of course by Sklar's theorem, basically we go through the machinery. So this is what we wanted to do. So we take some so-called marginal scores, MES, which is just a linear combination of the marginal scores of every single dimension. So and this is often done in practice as well. For example, also in the GEFCOM, and also in practice. So if you focus multiple dimensions, you just take the average across all horizon and all the single coordinates. And yeah, usually, of course, we don't prefer any dimension in contrast to the other one. Instead, just this kind of vector equal to 1. But here, of course, we can use every marginal score, and the most appropriate one seems to be the CRPS. But of course, you could exchange it. But within this paper, we are just considering CRPS because we are more focusing on the dependency point. And then, of course, you have a copula score. And this is nothing else than some multivariate scoring rule for the copula of our n variable. Okay, so what do we have? We have now the problem that we have the marginal score and the copula score, and we have to combine them to some extent. So we need somehow a mapping which goes from R, which is the underlying space of marginal score, and the copula score to R again, with a certain function which combines both scores and define a so-called copula. Oh no, not CES. It should be. Well, CES is already for the energy score theory. You define a joint score. Just considering this. If you do so, you notice quite quickly that G has to satisfy some properties. Maybe this inequality, which is basically the same, which has to be satisfied by every bivariate distribution function. But then the question is, well, how to choose G in practice, and this is something we did not cover that deeply. So there is much things to also improve. But
So the point is that it's just to make sure that your MCS is strictly proper, right?
Yeah.
If G is isotropy.
Strictly proper. We just had at the beginning two ideas, which are kind of thing you always come across. First is just add them, both scores. But if you add them, which is option A, you quickly notice, well, you have a problem because the copula has essentially no unit anymore, and the marginals are usually measured with a certain unit. So CRPS is measured in megawatts if your inputs were in megawatts, but the copula has no unit at all. But if you just scale your input data by 1,000, the copula stays the same, but the other part scales up by 1,000. So you have the scaling issue, and this quickly told us, oh, well, maybe this is not the best way to do. So we kind of skipped this additive approach, and so the next thing you think about is then multiplication. Also because of the thing, thinking about the multivariate, the bivariate normal distribution, we know that the correlation is measuring the dependency, and we know we can always multiply things with the correlation which has no unit and measuring the dependency. So this seems kind of intuitive to go for the multiplication structure. So to just take essentially the product between both scores. The only problem is this only works if the state space is positive in both cases. So this is a crucial point here. But for example, for the marginal scores that are usually applied, like the CRPS, this is not a problem. But it might be a problem for the log score. Log could be negative. However, so this is what we did. And then we have something, well, this is not really a theorem, this is more like a statement. If we have a marginal copula score, the result is strictly proper and it basically follows by theorems. So it's nothing special. Of course, we need continuous margins. Now going further, everything we will consider in this study right now is for the marginal score, we will only consider one score, which is a CRPS. But of course, here we have other options that are somehow related as well. And for the copula score, we will consider the energy score on the copula, the variogram score on the copula, and the David-Bastiani score on the copula. This is what we will do. Theoretically, of course, the log score would be another option to apply. And originally, so our core idea was, well, we think, or we were quite, I'm not sure, but we thought, well, it should be quite a good idea to apply the CRPS on the marginal scores, because there it works well, and apply the energy score on the copula.
I have a question. If people use a Gaussian copula, the three are equivalent, right?
This one?
Yeah. Wouldn't that be?
No. Because this tracks mean and variance, this only tracks variance, and this is.
Yeah, but if you have a Gaussian copula, everything becomes normalized through the transformations to marginal, so you don't care about the mean anymore, no? Also? Anyway, we can discuss it after.
Yeah, we might be right. So this is the setting, and to go further, we introduced the notation for now that uy is the copula random variable of y, so just apply the distribution function on y, and the small uy is the corresponding observation, so we've observed. But note, here's the true distribution. Okay. So now on a few properties of these corresponding scores. So we first designed the copula energy score. So the energy score applied on the copula. And basically we could just take this object here, like the energy score on the copula with the corresponding copula observation. But to make the score as sensitive in the relative change as possible, we kind of wanted to push this as close as possible to a zero, because we are multiplying in our score two scores with each other, and you know the multiplication has the largest slope around zero, so we wanted to go close to zero with this score. So we subtract the lower bound and multiply it with a constant which just takes care of the dimensionality of the problem. So this kind of is a dimension adjustment because this score grows with square root of h in the dimension. So this is what we simply did here, and we just choose this lower bound, which is due to a simple estimation on the inequalities, which basically is some Jensen and similar things applied. But we know that this bound here is not a strict bound, so we can do better. But so far we still have a proper proof for it. We just have it in a bivariate case, and we're still doing more things here. But at the end, it turned out that it's even not that important to go for the proper bound, and it would extend the paper so much that it's not worth doing it here. Anyway, so basically this is just the copula energy score. Then we have the copula barogram score, and here we have just the definition where we take the well, this should be the variogram score of the copula with some weight matrix. So this is the weight matrix we have in the variogram score, which is usually just chosen to be just everything 1. If everything is just 1 in this matrix, this product turns out to be h squared, which is just the square of the dimension. And also this more or less just kind of takes into account the increase in the dimension of the corresponding score and normalizes for it. So this is what we have. We have an upper bound, of course. Well, this is a simple upper bound, it's not the optimal one. What more important is we have a lower bound, and this lower bound is 0. So we don't have to do something like here with subtracting something. So we have automatically the lower bound at 0. Okay, this is the variogram score. Then the copula David-Bastiani score. Here we don't have any scaling in front of it because it's, well, we could do so, but this score is not useful at the end anyway for the things we wanted to do. The reason is that this expression here, of course, first of all, it depends on the covariance matrix and the mean of the copula random variable, which has, of course, which lives on the unit cube. So the mean is just a half, and the variance is also stable. So it basically just depends on the correlation structure of our copula. So it reduces to this formula at the end. And then it's quite easy to construct an example, maybe this one, for example, where for delta equal to 1, this thing has a determinant which goes to 0, and then you see here the log of something which is essentially 0 goes to minus infinity. So you're not bounded from there. So this score is strictly it's not positive. So it's not applicable for the multiplicative structure we have seen. What we also tried is to just take the exponential of this thing, but then everything exploded again because exponential behavior is not well behaved anyway. And, essentially, we know the David-Bastiani score is not strictly proper anyway, and just evaluating the correlation structure of our copula, so it's not. It's more for reference. It's not really for being the most useful thing. Okay, so this is what we have. So we have all the 3 options for the copula score. And now it's a problem about how to report the multivariate forecast. So far we just assume, well, we have our fx, so our multivariate distribution. But as mentioned before, this is not always often the case and not practical as well. But of course, if we have it, it's nice. We could also have something which is equivalent to it. So if you have a density forecast, it's fine. If we have a forecast of the characteristic function, it's fine. But in practice, it's often not the case. Therefore, basically the thing we kind of recommended to have an ensemble forecast. In the sense of that you just simulate many paths across your or from your corresponding random variable. In practice, of course, we have to do this experiment, not just one, but we have to do some kind of rolling window study or expand, but usually rolling window study. They kind of shift your experiment again and again and again, and create for every experiment a new ensemble that you record as your forecast. So this xi will be now for the i's forecast experiment, for the i's rolling window, the corresponding ensemble. I think I have a picture now. So basically what we have is, where we have some min-sample period, we estimate our model somehow, and then we have a forecast where we have a set of ensembles, then we do the evaluation, and then we shift everything and so on and so forth. Of course, this ensemble is very small, but this is the machinery we kind of suggest for practice. Of course, as mentioned, if you have one of these things available, you should not go for it. You should use these things directly. But still, then you might end up in some, you might have to solve some integrals and so on, which are computationally so heavy that it's even then not really feasible, and at the end you end up here anyway. Okay. So now about the estimation of the scores. For most of them, it's straightforward. For the CRPS and so on, we know this quite well. For the Mario Brown score, it's also basically everything can be estimated by the corresponding sample statistics. The only thing I want to mention is concerning the energy score. Remember, the energy score had this kind of two parts. The first part, which is the deviation from the observation, and then this dependency measure in the second part. And this part is quite straightforward to estimate as well, just using the corresponding sample counterpart. For the second part, it's a bit more, well, it's also quite straightforward to estimate. Basically, the thing which is most intuitive is to use this thing here with the k is equal to m, which essentially computes the distance between every simulated trajectory to another trajectory. But if we have, say, 1,000 trajectories, or 10,000, or a million, this is a huge amount of pairs, because it grows quadratically, and it makes the estimation of this object very expensive. But if you just have a small amount of ensembles, this is always feasible and recommended, because this has the lowest variance at the end. It's quite easy to show that then you should go for it. But in practice, if you have a huge amount of samples, we recommend to do not just the full triangle, but do something smaller, which would be something like a band around the center, or in the most extreme case, just evaluating the diagonal. Right? This is just to keep, to have fast evaluation methods. And our experiments showed us that basically, when you choose k is equal to 1 or 2, but basically just evaluating the diagonal, the estimation error or the variance of this part is basically of the same magnitude as this one. So going here for the quadratic effort, of course it improves things, but not substantially, because then this part is dominating anyway. Okay, so just as a side note for estimating the scores, so the standard multivariate scores. For the copulas, things are a bit more tricky. Why? Well, we have our copulas with the corresponding copula observations, but the problem is they depend on the true marginals. And of course the true marginals are unknown. So of course, theoretically, what you could think would be one approach, just to replace the true marginals by a corresponding estimate. The most straightforward estimate would be the empirical cumulative distribution function. Just by taking this one, or maybe a bit better is to take the midpoint rule, where the discussion if it's left continuous, right continuous, and you could take a mixture of both of them. But basically, it's almost the same. And if you do this, you get an estimate for the copula observations, just by plugging in them, which of course makes intuitively at least sense to just replace the Fy by the corresponding estimate. But the problem is, if your marginals are misspecified, you are in a problem, because then your copula will have misspecified marginals under the true distribution as well. So, and at the end it turns out even that you can even lead, if you just use this thing and apply our scores, you can get examples where you are getting a lower score just because of misspecified marginals, because you can kind of cheat somehow. So this is a problem, but it's not a big problem, because we can just force our marginals to be uniform while preserving the dependency structure. And this is usually done in this kind of copular literature by just using the ranks across everything. So what we do is we define so-called adjusted copular observations by just ordering them with the corresponding ranks. And we order them so that the observations afterwards live on this grid. So we force, basically, if we have some observations, we force them afterwards to be uniform by living on this grid. And this then has the property that the corresponding Kolmogorov-Smirnov distance of this uniform distribution is minimized. Because of whenever you force something to be on a uniform grid, you have several options. Yeah. You could, but this seems to be the most intuitive one. So if n is equal to 10, for example, to have one observation at a half, the next one at 1.5, up to 9.5.
So the fact that you are also penalizing the margins, is there like a balance? Even if you have some estimation error in your margins, but you are at the same time sending the error of the marginals, have you looked at maybe there is some kind of balance? Because if you have very bad marginals, you have high error here.
Well, but if you have very bad marginals, the thing which is relevant here is just giving the marginals how the marginals of two observations of two parts, how they are kind of ranked to each other. So if one pass has here in the upper tail, how it's afterwards in the lower tail, and the size of or the shape of the marginals itself is not relevant anymore. Now it's just about the ranks of the corresponding paths. Basically, you kind of remove the effect of the marginals and just look at the dependency structure. And for the copula, we can do exactly the same. We take the trivial copula, also by just taking the corresponding ranks. And yeah, it turns out that this method works. Then there's still a further problem, because well, we know this simple formula. The product, the mean of a product is the product of its mean plus the covariance, and therefore we consider the estimate of our thing we're interested in as the marginal score estimate times the copula score estimate minus its covariance structure. And this covariance we just estimate by the corresponding sample covariance. But then we have finally an estimate for our marginal copula score. And then we have everything we need for applying these things. So to the simulations, or to the applications, which is first just a simulation study. For everything we see in the next slides, we apply 9 scores. So the plane energy score, the Valgram score, David-Sebastiani score. Then the CRPS copula energy score. So the marginals evaluated by the CRPS. For the copula, we have copula score, the copula energy score. And then the next option with the copula Valgram score. As mentioned, the David-Sebastiani score did not work because it was not bounded. Then the single CRPS. So this one should always do well in the marginals, but nothing at all in the dependency structure. And then these 3 things, just to see how the performance works on the dependency structure. So just the copula energy score, copula Valgram score, and copula Davids-Bastiani score. So these 9 scores we are evaluated, and we are looking at 2 criteria for any score. One is the relative change in the score. This is the thing which Pierre looked at as well, also to see if we can replicate a study, of course, these kind of things. And then we are looking at the DM test statistics, which is essentially just a t-test and the corresponding test statistics. And we know, well, if it's above 2 or 3 or something like this, we have depending on our level. And the first study we are looking at is the study from Pierre, where we have the change in the correlation of a bivariate normal. And here we are considering a window length of 512. So this is the amount of observations we have. And the ensemble size is 60,000, so it's reasonably large. So, and now, yeah, don't be scared. But yeah, it was tricky to get it on, yeah, to present these kind of things well. But basically, these are the same plots as Pierre had in his graph. The only thing is we extended it not just from positive correlations, but also for negative ones. And yeah, and then we have here the correlation of the forecast, and here we have the 2 correlations. So if you take, for example, the magenta one, which is 0.8, so the 2 correlations 0.8, we see the magenta line has a minimum at 0.8, which is what makes sense. But if our forecast has a true value of 1, or has a value of 1, which is a weird one, but anyway, then we see the change in the score is maybe, say, 1%, which is also, say, the range which Pierre says in this study and was mentioning where this is very low. And especially if the true correlation is just 0, we see this curve is very flat overall. And the difference between 0 and 0.4 is hardly visible in this kind of plots. So, but this is what we have for the energy score. For the variogram score, essentially this paper just was built based on Pierre's paper to adjust for this correlation problem. And we see, well, this kind of seems fine concerning the relative change in the score. If we have 0.8, for example, we see the relative change in the score here is quite large. You see the magnitude is 1, it's 100 times as large as here. But we see we have some asymmetry for some reasons. This one looks very symmetric. So the behavior at 0.6 and minus 0.6 is basically the same, it's symmetric. It's not basically the same, it's the same. I can show it even. But for the variogram score, we have some asymmetry in here. Anyway, this is the score we have. Then the Davids-Bastiani score. This is always important for us here for reference because we are in a multivariate normal setting and we know this score should perform very well there because it's basically designed for it. And we see, well, at 0.8 we also see sharp differences and similar values than in the variogram score is for positive correlations. Okay, now look at the CRPS, TS, so CRPS and the marginals, copula energy score for the copula, and look at these 2 plots and they basically look the same, which somehow makes, well, what makes sense. They also look the same as here, because of course the marginals are always the same. So all the power comes from the copula energy score, which is just evaluated here. And this plot is really almost the same. You see here 0.4, 0.4. It goes basically in the same way. So it boils down from the performance from the copula energy score. And you see here now, well, here we have values of 0.4, whereas here we have values of just above 0.2. So it seems to increase this relative change in the score by almost 2. So it's not what we hoped for to reach something like this, but at least something. This is what was, or is the effect here. For the copula variogram score, we have similar things going on. As here, we have certain plots, and you also see, well, this is slightly stronger even than in the plain variogram score. Here you have to be careful, but looking at the blue line, for example, here it ends just above 2, but whereas this ends at 1.3 maybe. So concerning the relative score, the copula variogram score seems to detect the correlation change even better than just the variogram score. Okay, CRPS of course cannot detect anything. Yeah, it's also kind of measure for the significance bands indirectly, and the copula David-Soziani score seems to work as well. So, but this is just on the relative change in the score, and as was mentioned, well, the relative change in the score is not really the thing we should look at, and therefore we propose or we think doing some significance testing. Are you significantly better than the true model is the thing to do. And now look at the corresponding D-word Mariano test statistics. So, of course, they should be positive. They don't have to be, but they should be. And everything, say, above 2 or 3 is something like significant. Okay, so just look, for example, at 0, the most tricky case. At least it looked like this year it was the most tricky case. If we look at 0, and say our forecasted correlation was 0.4, then we have here a t-value or a statistics of about 4, and here it's just above 4. So we are clearly significantly different from 0 with a t-statistic or with a test statistic of 4. Well, this test is asymptotically normally distributed. So I forgot to mention this. Yeah, so this is we have here values of around 4. Looking now, for example, at the Variogram score, we see here at 0.4 we get values just below 4. Oh, here it's even clearly below 4. It's even below 3. So we see that concerning significance tests, the energy score seems to be even slightly better than the Variogram score, and this also holds for other parts, which is kind of surprising having the picture before in mind. Yeah, but this is. Now for the David-Soziani score, we know this would be the best one. Basically, we shouldn't be really able to beat it. Here we have for the 0 and looking at 0.4, for example, gives us here a value of just above 4, 0.4, somehow more above 4, 4.5. But still, it's not much better than the energy scores do. Energy score is slightly below, but not much. So it seems to be quite nice, the energy score, at least in this setting, concerning significance test. But everything, so all of them seems to work properly, also the Variogram score. So looking at the CRPS, CES, so marginal the CRPS and the copula score by the energy score. Here we have the 0 going to 0.4. Here we have a test statistic of 2.5 maybe. And on the other side we have also something like 2.5 or maybe almost 3. So we have still significance, but we are worse than everything else here. So we are losing some more things. When looking here, just on the copula energy score, we are somehow better, but worse than the energy score itself. So 0.4 goes here to something like 3.5. 0.4 is something like, okay, this is just above 4, but similar here. But in general, energy score performs better than the copula energy score. And the copula energy score is better in these kind of settings like this here. The reason is because, well, we still have to add the noise to some extent from the estimation of the marginals, and this is always not perfect, and yeah, here basically we have similar results. It works, but it's not better than the Variogram score, and even worse than the energy score. This doesn't work anyway, and here it seems to work as well. But having this in mind, the best score on this graph is the David-Soziani score, of course, which is kind of the benchmark because it's designed for it, followed by the energy score through all the settings. Okay, so this is for this experiment. So let's look at a slightly more sophisticated experiment, which is somehow related with a very similar setting. So basically this is a study which was similarly used by the guys who introduced the Variogram score, but we kind of adjusted it to some reasons, but basically, and extended it. We consider again a multivariate normal distribution, a bivariate one, with a certain correlation. And then we have this true setting. We consider here rho equal to square root of 2 over 2, which is something like 0.7, which is a correlation which is but extremely heavy, but not extremely low. But 0.7 is something, well, we can always accept as a kind of standard measure. Then we have this as a true setting. Then we have a symmetric mean bias, so we just shift our mean. Then we have an asymmetric mean bias, so we increase one mean component and decrease the other mean component. Then we have one setting with a smaller variance, we just scale the variance down. One we scale the variance up. A next one where we reduce the correlation, and another one where we increase the correlation. But how? And this was done for some setting, at least in this study, this Varigram paper study as well. But they shows these kind of shifts just ad hoc, just some values. We said, well, but this is, we want to have something comparable. But what means not sensitive in the mean, in the variance, and so on. So we decided to go for changes in the likelihood. So we kind of choose these kind of parameters, A1, A4, and so on, so that the likelihood reduction from the true setting to the other settings is in all settings the same. So this is the approach we went for. And when doing so, of course, you have 1 degree of freedom. You can choose how much you want to change. And we went for choosing A5, which is the smaller correlation part, equal to 0. So from this 0.7 up to a correlation of 0 is the kind of the benchmark. And this gives us directly, this is a likelihood reduction of this number. And based from this, we can compute the values for the other ones. For some, we don't have explicit solutions, but it doesn't matter. Okay, so we do this experiment. Ensemble size is now 8,000, rolling window size 256, and we replicate these experiments in total 64 times. Yeah. So we have the rolling windows going 265 times. We are getting at the end the test statistics. This we are keeping in mind, and we are repeating everything 64 times. And now look at the corresponding plots. Now we have the box plots of the corresponding means. Well, it's hard to see, but I will explain things for the corresponding setting. So the first one is the true setting. This is, well, it's 0. We could remove it from a plot anyway. Then we have this symmetric mean shift. Then we have the asymmetric mean shift, the smaller variance, greater correlation, smaller correlation, and greater correlation. The same ordering as we had, as I just presented. And then we have, again, the relative change in the scores. And here we see again what Pierre was observing. Well, for the correlation, the change in the score is quite small. But especially if the correlation increases, it's hardly different from 0. It's hard to see that it's even above 0. In contrast, the Varigram score, we know for symmetric mean shifts, we don't see anything. Well, it cannot detect it. But for the remaining part, this seems to be quite fine. David-Sebastiani score, well, what we see is we have always the same level of shifts, which kind of says, well, we did correct in the computation here, because otherwise it wouldn't be the case. Yeah, this is also quite nice to see. Yeah, and then basically the other plots, and what you see, the copula, the CRPS-ES has basically the same pattern as the copula energy score. Well, and these kind of bars shifts a bit up, so it's more sensitive, the same as we have seen before. But yeah, this is what we get at the end. You also see, well, the CRPS can detect changes in the marginals, but not in the correlation, and the one on the bottom detect changes in the correlation, but not in the marginals. Okay, but this is just a relative change in the score, and we know it's not worth looking at it anyway. So let's look at the test statistics. What do we have for the test statistics? Maybe first looking at the David-Sebastiani score, because this is kind of the optimal benchmark. What you could expect is that kind of this pattern preserves, but it's not the case for some reason. So the test statistics are not, say, all at the same level. And for the David-Sebastiani score, the most tricky part is to detect the greater correlations, which is has a t statistic of about, or a test statistic of about 4 to 5. So this 4, this 6, so this is 5. But it works quite well in all these settings with test statistic between 10 and 4. Looking at the variogram score, we see, well, change in the mean, we cannot detect it. But for the other parts, well, this is 5, this is 10. We have values, say, this is around 3 to 4 maybe, for some settings. So we can detect some settings quite well, even better than in the energy score. For example, the energy score has struggles most with greater correlations, similarly than the David-Bastiani score, with t-values up around 2 to 3 maybe, whereas this has a value above 3. But the variogram score was designed for catching changes in correlations. Energy score can catch everything. But of course it works everywhere, similarly as the David-Bastiani score. And in general, it has here a very similar pattern. Basically just all the values are a bit smaller. So.
Florian, for your visualization, I don't understand why you don't fix a significance level and then look at the percentage of time you reject, for instance.
Well, of course I could do so, but then if I look at the distribution of the test statistics, I get a much better feeling for really what's going on.
Sure. Yeah, for us, but I was thinking more for say your clients, if you want to show what's going on.
Yeah, well, this is also what we thought about. But it's tricky, Yeah, but maybe you're right, but then you should need likely more significant levels, and then you get again plenty of plots or tables, and
I was more, you just fix one and to give an
but then you can't distinguish, say, then all these one are the same and these one maybe fail, or here you really see, well, this is performing quite well in catching the correlations, but really failing in the other ones. Concerning the CRPS-CES, it has again similar structure than this one, but the significance level again reduces a bit. So here we just have values around 2, so just hardly significant. It seems to work, but again we are losing power compared to the energy score, which is again worse than the David-Bastiani score. But still, this one seems to work, which is fine. Somehow interesting is, of course, the CRPS-CES is like a mixture of this thing. So you see here these 4 bars, which goes into here, and these ones.
So that's what I'm not sure. I mean, because if you say it worked, if you say it's 4, the level that corresponds to a certain level of significance, with your energy score, I mean, you correctly reject what? Not even 10% of the time. No, I'm looking at the very right one.
Yeah, this one.
So you correctly reject 5% of the time or 10% of the time?
Yeah, maybe something like this.
So it's but of course very powerful. I mean.
Well, it depends on the significance level, and of course it depends on your rolling window size. If they would just double this, of course, then every value would just increase. Therefore, I think the relative picture is more relevant than just saying, well, this rejects that often and that often. And I think it's worth having the relative picture compared to the David-Bastiani score. And we see we are losing some power here. We are around 3 in average, and this thing is around 5 in average. So this is the thing we have here for these test statistics. And now the last experiment I'm going to show you, which is basically the thing I think Steve left us. Steve mentioned this peak thing. He mentioned, well, it's hard to beat the flat forecast just with point forecast. And this study is basically motivated by this thing. So what we have is a so-called random peak study. So just imagine there is, I don't know, someone who gets up every day and uses some electricity, but always when he has his shower, electricity demand goes up a lot. And we know the guy has always, every day he has a shower when he gets up, but we never know when he gets up. Maybe it's at 6, at 7, or at 8. And maybe it's uniformly distributed across these things. And this is the setting we are having here. So we are having a kind of underlying basic noise, like this yi, which is just the standard normal distribution. And then we add some peak at one uniformly chosen coordinate. So this is just the vector which is 1 in the first coordinate and 0 in the ones, with a certain peak shift of here magnitude to Q. So this is the true underlying distribution. So we have every time we have a peak, but we never know when it occurs. So and then we have a couple of models which kind of should try to get this thing as good as possible. One thing is the average mean. So it's just a normal distribution where the mean corresponds to the average mean. Then we have the so-called fudge forecast, which just estimates 0 all the time, like having never a shower. Then we're having a fixed peak. So basically, this is a distribution, or this is the case where he always has a shower at 6. A rolling peak, where on one day he has a shower at 6, the next day at 7, the next at 8, then again at 6, then at 7, then at 8. So across the rolling window, this will get the correct marginals, but of course it's definitely not correct. Then we have a mixture normal distribution, this has exactly the same marginals as the one on the top. But here, basically, what we have is it might happen that sometimes he has twice a shower, or some days where there is no shower at all. And so this is a characteristic of this mixture normal. Then we have a shifted mean, so that just the same setting as above, just with a shifted mean. And then we have a multivariate normal distribution, where the mean and the covariance metrics correspond to the true setting. So if you compute the mean and variance from this setting here, you get this thing. So these are the models which compete against each other. And of course we know, well, shifted mean by a ground score should struggle here. Normal with true mean and covariance metrics the same, the David-Zastiani score should struggle here. Mixture normal with same marginal distributions, the CRPS should struggle there, because the marginal distributions are the same, but the distribution is not, the dependency structure is not covered correctly. So this is what we hope to see. We first consider just the 3-dimensional case and the peak size of 5. So if the other part is normally distributed, this is clearly usually often well visible peak. Ensemble sample size 16,000, rolling window size 32, so not that much. So 32 observations is not a lot. And we replicate everything again 64 times. But now I'm just showing the DM test statistics because we know the relative changes. Okay, again the same similar plots as before. What do we see? We see here the energy score. And here we have the test statistics, so this is 5. So here we have something like 2.5. And we see that's always above, so the mean is at least above 2.5. So we can detect the changes even though we just have 32 observations in all settings. The easiest settings are the changes in the mean, but this is holds basically for almost everything. And the more tricky part are the fixed peak, rolling peak, and the mixture normal. So here, energy score struggles most. If you look at the Vargram score, it fails, of course, for the shifted mean. This is what we expect. But also for the multivariate normal distribution, it seems not really to catch this difference properly. Now you see it goes slightly up, but it's just hardly above 0. And also the other ones are not really great. Yeah, so you see they are worse than the energy score in the other settings. So here we have a value of 4 on average, and this is 5, this is 3.5 maybe. David-Zastiani score is in most settings quite fine. Yeah, score is always above 5, except the multivariate normal case when that fails. But for the other one, it's not too bad actually. Yeah. Looking at the CRPS-CES, well, we see a similar picture than here. Well, not too similar, but we see that it works somehow as well. But the test statistics are just above 2 in the most difficult cases for the score. So just say, not really, maybe a bit significantly different. So it seems to work somehow, but not as good as, for example, the energy score. The CRPS copula Vargram score is even worse. So here most of the values are just below 2. So this does not seem to work properly as well. And basically, this comes also from this plot here. You see the copula variogram score has not a great performance at all. Basically, nothing is significantly different from 0. And for the copula energy score, the picture is quite similar. Only maybe one case, and this is the mixture normal, which has the same marginals, but different dependency structure than the true setting. Here he is able to catch it quite okay, say, but even not that good. Yeah, this is the picture we have. And of course, CRPS works fine. It's basically almost the same properties as the energy score, except for the setting with the same marginals. But these scores here are on a similar level. Here it's even a bit better, but the magnitude is the same. So, summarizing this picture is basically energy score performs the only thing which catches everything, maybe the CRPSC has as well, but this one is much stronger than this one. The other ones fail at least in one situation.
I'll just check I'm interpreting this right. So as well on those, the energy score one,
Yeah.
the flat forecasts are performing worse. Are we saying that the flat forecasts perform worse than the ones where you at least put the peak somewhere? Is that a correct interpretation?
No. The plat forecast says, well, he's never having a shower at all.
Yeah, no, I understand that. So, but what I kind of like to say is that the guys who predict that there is a peak should beat the guys who don't predict a peak at all. Is that something
well,
that
this
you
is the
think of
case.
that measure as
So,
well?
these ones, the first two guys, they never have a peak.
Yeah.
And you see, well, their statistic is much higher than the other ones. And the other ones, they have somewhere some showers.
Right.
Sometimes twice, sometimes never, but here they have a shower, so they are all better than this one.
Okay.
So this is what we see in this picture as well. Especially the guys which have always a fixed peak. Actually, it's quite tricky for the energy score to evaluate that this is really a bad forecast having the shower always at the same time. Okay, but this seems to be the best case, and this is not a setting which is designed for multivariate normality. This is a slightly more tricky situation, which especially concerning smart meter data and so on is, I think we should have in mind something like this. Okay, now we have two variants of the thread experiment. The first one should look at the effect of the ensemble size. So when we increase the ensemble size, what is the effect on the test statistics? Of course, we know in practice we should have as many ensembles as possible to reflect the true and distribution property, but we can never do so. And we wanted to know, well, what is the effect of the ensemble size to understand, well, should we take 10,000, 1,000, 1 million or not? So this is what we did. Unfortunately, just up to 16,000 because then computations get very heavy at the end. But still, we see some things. And afterwards, we see we look basically at the same experiment, but increase the dimension from h equal to 3 to its square to 9. To see what is the effect if we increase the dimension of the problem. Okay, but first look at the A. So what you see now is just, well, here we have seen these box plots of all these 64 replications. Now we're just looking at the mean of this thing. Okay, for every part we are looking at the mean value for all different number of simulations, so the ensemble size. This is the energy score. What we see is if we have very small number of simulations, most of the, or at least some methods fail, but some already work quite well. Even with 16 replications, for some, we can detect these things, which is kind of nice. But especially for the two tricky cases, the mixture normal and the multivariate normal with the same mean and covariance structure, we need quite a substantial amount of observations to get to significance. Here I dashed the two to see somehow say significant. So this is what you see, and you see, well, it needs some time to kind of stabilize, because we know at some level it should stabilize. And we see here, well, at 16,000 maybe it just reached, but maybe it increases even a bit further. Whereas, for example, for the situations with the average mean or the shifted mean, it seems to stabilize at around, say, 1,000. So there, 1,000 simulations would be completely sufficient to show significance, to show that this model is significantly different from the other ones, but for the complicated ones, we can increase the efficiency of our test just by increasing the ensemble sample size.
Can you do this incrementally, incorporating additional trajectories until
Yeah,
you
you
see
can.
the stabilization?
You could. Yeah. Of course, strictly this would turn into a multiple testing problem. But if you will ignore this problem, you can do so. But interesting is, for example, that for the fixed and rolling peak, with 16 we have a certain level which stabilizes all the time. So you're not gaining anything from adding more samples to it. So it's completely different behavior we see here. So it's not clear at all what we get from here, just that in some complex settings we need quite a lot. This is what we see. And looking at the other ones, it depends on the score. For the David-Bastiani score, for example, which just evaluates mean and variance, it stabilizes quite quickly. So here just maybe 500 is completely sufficient to catch all the information from the things you want to evaluate. Well, and the reason is the David-Bastiani score just looks at mean and covariance, and this is quite easy to estimate. And mean is easier than covariance, and this is also why you see, for example, the model with zero mean increases at the beginning, quite strictly, and then it stops here. Now maybe at 30, 60 values. Well, it's difficult to see, but it's in there. But also the other mean models, so they stabilize quite early. But the model with a mixture normal model, where the covariance structure is more relevant, here he needs a bit more time to get stabilization. So it somehow makes sense to see these kind of pictures. But basically that's the most important part. One thing I want to point out is on the copula energy score, you see it's not working well. Everything is below 2. We see the sample size, it might increase further because we are we are even in an increasing pathway, but we would need to get this working properly a huge sample size to get stability in here. So this is somehow a problem, but still we see in general the method seems to work. So we kind of are on the right track and see that we detect something at least. And of course this CRPSC has similar pathways. Maybe just a note, the CRPS also is quite simple, so you don't need that much simulations. And the reason is, of course, well, you're just evaluating univariate marginals, and they are maybe having thousands of observations, that's already quite fine. So you're not gaining that much by adding more if you're just looking at the marginals. Okay, but now let's turn to the dimension impact. So now the problem is not 3-dimensional anymore, but 9-dimensional. So much larger space. This is again the energy score, and again it seems to work. You know, we're getting, so maybe just having in mind here we're getting above the 2 at this stage, and then later on. Here it's somehow similar. We are getting above the 2, but later, which makes sense because we are in a higher dimensional space. But still we are managing to kind of reaching a point where we can detect the differences. Whereas the other settings mostly fail completely. Even the David-Bastiani score is not doing very well here. Also takes a couple of time to converge. But the thing I want to point out most is the copula energy score here. What you see is basically nothing. You see, whereas here we still had this increase, we were able to catch something at least. Yeah, here we are not able to catch anything. Yeah, so completely disastrous, even though it's 16,000. We know it's strictly proper, and with a sample size large enough, we would catch everything here, but we are not getting anything. And the reason is just the sample size is too small. And why this is kind of interesting, what makes the copula energy score so much worse than, for example, the energy score? And this is not easy to understand, but the reason we will kind of discover soon in a few slides. So this fails completely, contrast with this. Whereas in the three-dimensional case, it's still okay. So okay in the sense that we detect at least something, but not by far not as good as the energy scores. Okay, so conclusions from a simulation study. So at least what we get from this, we think that the energy score is the only considered score which seems to be suitable in all settings. Yeah. Maybe not always the most powerful. Yeah. So in some cases, some scores are slightly better, but never really extremely much better. Somehow a bit better in some settings, designed for just correlation or something like this, but never extremely powerful. But why the energy score is so powerful in this meaning? Especially that it preserves all these properties even in quite high dimensions. Yeah, so 9-dimensional is not huge, but at least something. And the reason it goes back to the structure of the energy distance. The energy distance is basically just the same as the energy score, where we just don't observe the y so far. So we define this distance, and if we observe the y, so basically we just add this term for the y, this is everything which changes, then we are getting directly to the energy score, because this one turns to a small y, the observation, and this one vanishes. So this structure is the energy distance, and this energy distance has a couple of nice properties. Of course, it's zero if and only if the distributions of both coincide, so we can distinguish them properly. It's also metric and so on. But the most important part is there is a way to rewrite the energy distance. Namely, it's a weighted two distance between the characteristic functions of both random variables. So the distance of x and y, this is just a constant, ignore it, is an integral across the characteristic function of x minus the characteristic function of y. So here we are in a complex plane, taking the absolute value or the modulo of it, square it. So this is the L2 part. And then we are integrating across Rz with a certain weight. And again, having beta equal to 1, but still this is just a weighting function. So the only place where the x and the y goes in is here, basically the distance between the characteristic functions with a certain weight. Why this is very special? Well, if you consider this distance just a constant, then a weight function times the L2 distance between the two characteristic functions, and you're looking for a function psi so that the resulting distance is scale equivariant and rotationally invariant, so you can scale your inputs and you're having the same ordering, and you can rotate in this multi-dimensional space, so multiplying with orthogonal orthonormal matrices, you are preserving the same distance. So this is, if you want to have this property, only this choice gives you what we are looking for. And this is exactly our energy distance. Okay, this is something very nice. Why? Because the energy distance measures effectively the distances between x and y, which live in an h-dimensional space, in C, which is the part here. Because characteristic functions, even for a high-dimensional vector, even for processes, they live in C. And if you have a distance in C, you're isomorph to R2, so you're living in fact in a two-dimensional space for measuring the distances. So intuitively, the energy distance should be quite efficient if the dimension is larger than 2. Because in fact we're measuring distances in C instead of RH, which is usually the case if you have some integral across RH. Of course, we also have an integral, this should be an H. If we have an integral across we have an integral across RH, but this is just for the weight, and the real core places makes sense, goes here into the life. And this is something quite nice, and I think this explains well, it's of course not a mathematical explanation, but why the copula energy score here fails completely, because here we have to explore a 9-dimensional space, which is extremely complex. Yeah. But the energy score, in fact, has only to explore a 2-dimensional space. And this is the thing which I think is very, very nice about this thing. Some more properties about the energy distance. It is quite powerful. So when I read it the first time, I thought, well, why this is not more widely known in the community? That was my feeling, at least. I'm not sure if someone here knows about this thing. But it allows, for example, arbitrary two-sample tests. So if you have one sample from one distribution, or one sample and another one, you can compare if they're equally distributed or not. You can also, of course, test against a specific distribution. And in the papers where they derived this thing, they did it for the multivariate normality. So, of course, this is very, this thing has a non-parametric nature, but of course you can plug in for the wider multivariate normal distribution and then construct a test from it. And if you do so, you are getting a test which is more powerful than everything else which is usually known in the literature. And this is quite interesting because it comes from a non-parametric setting at the end. And then this thing is the most heavy thing. It allows the construction of so-called distance covariances. So think about beta equal to 1 all the time best. The distance covariance is nothing else than this object here, which is in fact a weighted L2 distance between the joint characteristic function minus the product of the characteristic functions on its own. And we know, well, two random variables are independent if and only if the product of the joint characteristic function is the product of the joint characteristic function is the product of the single ones. So this thing allows to construct tests for multivariate independence, not just correlations like this, independence. Yeah. When I studied statistics, my professor said to me, well, it's impossible to test for independence. Now I know, well, it is. Yeah. But just many people don't know about this thing. Okay, yeah, so this is just a kind of side note on this energy distance. I think it's quite powerful. You can even generalize these things because, of course, here we have this beta thing. Here we have just the Euclidean norm to the power of beta. You could think about more general functions, other functions than just power of beta. But basically, you are staying in the same world when you generalize these kind of things with other monotonic transformations. Okay, now I just show finally one real data example for a data set you likely know. This is the airline data set, quite often used for illustrating some things. And here's the full design. We do a very small experiment, just 19 replications, 19 rolling windows. We forecast always a year and shift this then by half a year. So this is the setting we are having here, giving us in total 19 samples. So this is the thing we want to conduct. We consider in total 9 models, which are in fact 3 models with 3 versions of it. So just a simple AR12 and AR13. At an ARP where the P is selected by AIC using, everything is estimated using Newton Walker. Very simple and straightforward. Then we consider versions of these 3 things, namely the first one where we kind of force the error term or the residuals, whatever you want it, to be comonotone. So they're perfectly positively correlated. And this should be, and this one where they are counter-monotone. So they are completely always the opposite. So easiest thing is to look at this graph. So this is the standard ARP process and the corresponding sample path simulated from it. The comonotonic thing, where you have the maximum Frichet copula assumed on the residuals. If you're once on the upper path, you are staying there, and the lower one stays here. And this is where once you go down a lot, you go up again. And so on. But the important part is they all have the same marginals. Same marginals, but completely different dependency structure. This one, of course, is the most realistic one, but this is just to show well how these kind of things work. So yeah, we are considering this experiment with 19 replications, with 19 rolling window size, and the ensemble size here is quite large, 65,000. I'm just showing you now this is the average scores from all these methods, these underlying methods. And here we have the scores that we considered so far. What we see, so I first look at the energy score because I trust it most for some reason. And I see, well, the energy score prefers the AR12. So I would say, well, the AR12 is the model to go with. But the Variogram score, for example, says, well, no, this is quite right, it's not good. I prefer the ARP. I think ARP is the model to go with. And the second model is the ARP with quantum monotonic residuals, which is something like this, which is a bit weird, but this is what the Variogram score is selecting as second best model. Anyway, what we know from this is that even the AR12, I trust most energy score is not the perfect model, because the perfect model should score well in any score. And this is very important to remember. So it's worth having this information, so we know, well, there is some space for improvement, especially concerning likely the correlation structure, because the Variogram score is catching the correlation structure, and it prefers another model in contrast to the energy score. So there should be a model with better correlation capturing than the AR12, but preserving the other models, the other properties, which were measured by the energy distance. Yeah, and maybe quite interesting is that, for example, the David-Sebastiani score prefers the AR13. So he thinks, well, this thing is the best. But still, the difference is not that large. But this is not about significance, it is just having the point values. What is also interesting to see, well, the CRPS, we see all these values are basically the same, which shows us what the construction makes sense. Okay, but this is one thing, of course, which you can do and practice all the time. Now let's look at the significance results concerning the energy score. So basically, this column here, now evaluated with really significance tests. And what you see here is the corresponding test statistics with, I think, the p-value given in the squared brackets below. And then you see, well, the AR12 is significantly better than all the other ones. Not highly. Yeah, I have one slide. One thing I want to mention finally is, of course, we cannot just test one score. We, as seen with the Variogram score, it's worth having a look at other scores as well. And one thing I recommend for in practice is to not just use a multivariate score, but also back it up by low-dimensional scores. And one very simple thing to do, of course, is just evaluating the CRPS across the forecasting horizon. So looking for every coordinate where you're doing well and not so well. So you can easily detect, well, if there is a model better in some coordinates, you should, and say your favorite model is AR12 because you're doing here quite good, but here at the beginning you're doing worse, so you should improve there. So you can get quite nicely where you should improve your things. And the same holds for the bivariate copula energy score. So the copula energy score is measuring only the dependency structure. And if you take the bivariate copula energy score and you roll it across the focusing horizon, so looking at the dependency structure of the first and the second coordinate, and then on the second and the third one, you can explore quite well how good you capture at least the two-dimensional dependency structure, which is in practice the most important one. Of course, with the correlation, that is the most important special case, but something which is most relevant for us. So this is quite, of course you could increase this, but then the problem is in the three-dimensional copula energy score, you're having also the effects of the bivariate. So I still don't know a proper way how to only measure three-way dependency structures without having the two-way dependency structure. But that's essentially it. So overall summary, the energy score seems to be suitable for multivariate forecasting evaluation. If you combine it with significance testing, that's very important. You've seen that the ensemble size should be as large as possible. but I think it should be never the case that it's extremely large, because we are in fact measuring in a two-dimensional case, namely in C. And additionally, consider low-dimensional evaluations on the low-dimensional scores, especially the CRPS in these dimensions and the bivariate coupling dimension score. So this is what. Thanks. Sorry for being talking so much.
Yeah, so it's more that we have to start a bit earlier this afternoon, as we have to leave this room. It was 3 p.m., right? When we looked at, you forgot? Yeah. When we looked at the schedule the other day. So if we want to leave enough time for Swahili, we'll have to start.
My presentation is short, so we
okay,
should.
okay. So okay, but so then we have time. So I don't know if someone had some more questions. We had a few discussions during the talk, so I don't know.
Should I find a question?
Yeah, no problem.
I think a nice comparison we could do is with the log score with the copula structure, because in that case, the log score will be the log of the copula density plus the sum of the log score of the marginal set.
But there are hardly any models where you have the density of the copula.
Yeah, so I'm not sure in the normal case what can because here you did some simulations with the normal distribution.
Well, except for the third experiment.
Yes, so I think it would be a nice comparison, because then you can compare your score with another one that does the same thing, like separate copula and margins, because the others don't do that.
Yes, but at the end it turns out that the separation is not worth it anyway. So my recommendation in practice is, because also this function G, this combination thing, is hard to work out. It's much better to just look at the marginal separately and at the dependency evaluation separately. So of course you have to do then more things, but this is the thing I think to do. Of course, the just looking at the energy score is, I think, quite an efficient way to catch these kind of high way dependencies. So which you only can get like in the simulation study, like this 9-way, in the 9-dimensional case, 9-way dependency structure. There the energy score can do the job. Of course, the copula energy score could do the same, but has a problem that it's integrating across a 9-dimensional space. The energy score, in fact, not. So this energy score can do these kind of things. And for the low-dimensional marginals, the other things work quite fine. So you can deal with CRPS or any other univariate score. And for the bivariate case, there I think the copula energy score is a quite good choice. Just the bivariate, because in the bivariate space we can explore it quite okay using reasonable amount of simulations.
Yes, and a final comment. So many people are interested in these multivariate scoring rules, but maybe there is like a fundamental problem with this, the fact that in any case you are trying to compute things in high dimensions, so we should maybe do some kind of, it's like in high dimensional regression, the only solution is go back to something low dimensional by assuming sparsity and all that. So here, maybe in order to avoid these kind of problems, maybe we should have like some kind of dimension reduction in the score in itself or something like this. Can you comment on this, or do you think it's?
Yes, of course, but I'm not sure if it's feasible. Think about a problem where you have a strong, say, 6-dimensional interaction, which is heavily in the data, but it's hard to detect. I don't know any way how you could reduce this thing. Maybe if this dependency structure has a special shape, you can kind of map it into a lower dimensional space. But this would be then very tailored for specific effects. But this would be very tricky. I think one of the lessons I learned is that, so at least my idea is we should more look at the characteristic functions of the guys. It sounds a bit weird, but I think it would be best if we report our forecast as a characteristic function.
Oh, interpretability. That's best.
Yeah, but yeah, it sounds a bit weird, but why not? Yeah. Well, just an idea, because if we really go for the energy score, which lives on C and evaluates on C, then we could just report our forecast just this level. But this is just what I. Yeah, but of course, if you have the full distribution function, density, and so on, then you can always compute your characteristic function. But then you might have even better ways to approximate these kind of integrals.
Well, let's go for lunch and we'll discuss it there.
Yeah.
Thank you very much once again. Oh, you had some more questions?
Well, I have a question about non-continuous number.
Okay, so we can go for